K1, K2, K3, K4 values are given. So now see, very important. What are the units of torsional stiffness? Newton meters per radian, right? Now these methods are very important. Now what we have to evaluate? Now we have to evaluate, like, we have to prove that for this system, right? By using the concept of Holzer table, by using the method of Holzer table, uh, we have to prove that 1 radians per second is the natural frequency of this rotor system, right? Uh, so now the concept is, if no, if actually 1 radians per second is the natural frequency, it's very easy. Here you have to get 0, that is the V, right? Here that means, like, at this cell, if you cannot get 0, that means 1 radians per second will not be the natural frequency. Now let's try to fill it. So now we have to sketch the table like that. Now I stands for the rotor label, not capital I. The simple I stands for the rotor label. So how many rotors are there? 5 rotors are there. Wait. 5 rotors are there. 1, 2, 3, 4, 5. And then capital I, this suffix I stands for the moment of inertia. 1, 2, 3, 4, 5. See, moment of inertia also given, right? So you don't have to worry. And this cell is the rotor label, like the moment of inertia of the rotor times omega square. What is omega? Angular frequency, right? But now in case based upon the angular frequency that you are going to use here, if you are getting 0 here, that means that particular omega is the natural frequency, right? But here we call it omega. Carefully see the units, right? Very important. So now you know I1, not I1. Now here you know the moment of inertia and you know omega. What is omega? Omega is 1. Like that is the question given in this. Like that is the problem, because we have to evaluate that omega is the natural frequency. So that means let's consider omega as the given one, right? So omega squared times moment of inertia, this will be the answer, right? See, I, you know, omega squared is 1 because omega equals 1. So 1 times 1 is 1, 2 times 1 is 2, 3 times 1, like that you can fill. Now carefully focus this one. What is this one? Radiant, the amplitude guy, right? What is this one? The amplitude guy. The first amplitude we make it 1. Okay. What did I say? The first amplitude we make it 1. And to find other amplitudes, that means how many amplitudes that we have to find? A2, A3, A4, A5. To find other amplitudes, now if you do it from the long method, the conventional method, it will take, I don't know, like, it will waste your time. So in that case, now see, you have to use this formula, otherwise it is wrong. See, now this is the formula, right? That means, now see, AR plus 1, that means R plus 1th amplitude equals AR, means the previous amplitude minus 1 divided by torsional stiffness of the rotor of the rth rotor. That means 1 divided by KR means torsional stiffness of the rth rotor times sigma notation. Now you know that in sigma notation you have to give starting from which one and up to what value. I think this sigma notation is like familiar with you, right? Starting from I equals 1 till R, till rth element, right? Till rth guy. Okay, times what? Capital I, simple I means that this stands for that moment of inertia, omega squared AI. That means, let me teach you that. Now see, now say for an example, here you are going to evaluate A3. That means here you are going to find A3. A3 means the amplitude of the third rotor equals amplitude of the second rotor, because now if this is 3, this must be 2. Amplitude of the third rotor equals amplitude of the second rotor minus 1 divided by torsional stiffness of the second rotor, right? Times sigma starting from the first rotor till second rotor. Is it clear? Starting from first rotor to the second rotor, and up to second rotor you have to write first one I omega squared AI means moment of inertia of the first rotor, omega squared times moment of moment of inertia. I will tell again. Moment of inertia of the first rotor omega squared times amplitude of the first rotor plus moment of inertia of the second rotor times omega squared uh, times amplitude of the second rotor. That is the V. Agree? So that means if you are going to calculate A3, or if you are going to calculate the amplitude of the third guy, you must know the amplitude of the previous guy. Let's do another one more example. Let's say you are going to calculate amplitude of the fifth one. That means here A5 equals amplitude of the fifth rotor equals amplitude of the fourth rotor minus 1 divided by torsional stiffness of the fourth rotor times. Now carefully see sigma notation, right? That means I1 omega squared A1 plus I2 omega squared A2 plus I3 omega squared A2 plus I4 omega squared A4, right? I hope you know that. So now then you can evaluate this guy. Then if you know this guy, you can fill this cell also. Why? Because now you know I, omega and A. So what is the next thing? Then you have to find the sigma scenario. Now you know what is sigma scenario. Now consider when you are going to fill the first cell over here, right? When you are going to fill the first cell over here, right? Just consider the summation up to here. When you are going to fill this one, what is the only I omega squared A guy that you know? Only this one. When it comes to here, you know both of these, like this one and that one. So what is the summation? 1 plus 0 is 1. Agree? So when you're going to fill this one, then what are the things that you know? You know this one and this one, right? When you're going to fill this cell, only thing you know is that. When you're going to fill this one, only thing that you, not only thing, then you know both these guys. When you're going to fill this one, then look at your left side, you know up to here. When you're going to fill this one, you know up to here. When you're going to fill this one, you know up to here. Now see, up to here 1 plus 0 is 1. Then 1 plus 0 plus minus 3 will be what? Minus 2, right? Then 1 plus 0 minus 3 minus 1 means 4 minus 3 is 1, 1, 1, 2. Then up to here 2. Then when you are going to fill this one, positive 2 plus negative 2 will be 0. Now you know that, right? Now you know that, right? So now here don't worry why we have shifted this ki to here, because the reason that we have shifted ki to here means this is the portion that we need it, right? And also we have to fill this guy also, right? What is this one? Look at the last one. 1 over k, this must be 1 over ki, right? Right? Torsional stiffness of the ith rotor, right? Right? Torsional stiffness of the ith rotor times sigma capital I one. That means the moment of inertia of the ith one omega squared amplitude of the ith rotor, right? Simply add this. See this suffix I, yeah. Okay, right. So that is that side. So everything clear, right? So now see, you are getting 0 here, right? So that means if you are getting 0 here, right, then no problem, right? Then no problem. This 1 radius, then 1 radians per second is definitely the natural frequency. Now just consider. Now just consider, if you have considered omega as 0.98. Now see, then you are getting a positive balance. Focus problem here. Now see, if you have considered omega equals 0.98, which is lesser than the natural frequency, then you are getting a positive value here. And consider here you have taken something little bit more than the natural frequency, then you are getting a negative balance, right? So that is the scenario, right? So this thing, now this part you have to fill manually. See, that is the V, right? So I hope you got the Holzer table method, right? Thank you.